Hi, this screencast is on calculating the average atomic mass. So we're going to start by taking a look at relative masses. Understand that the mass number that's reported on the periodic table is the weighted average of all of the naturally occurring isotopes of that element. Now we find the atomic mass of each element by adding the number of protons and neutrons. But because there are isotopes that exist, so atoms of the element that have a different mass because they have a different number of neutrons, that means there's more than one mass to average for each element. So we're going to make an average of all of the naturally occurring isotopes, but it's a weighted mass, which is what's reported on the periodic table. Okay, so it looks at not just what are the different masses, but how much of each of those different masses exists naturally in nature. So scientists use a standard to compare units of atomic masses, and that's based on the atom of carbon, so carbon-12, and it's just been arbitrarily assigned a mass of exactly 12 atomic mass units, or 12 AMU. So one atomic mass unit is exactly 1/12 the mass of a carbon-12 atom. The atomic mass of any atom is determined by comparing its mass to the mass of carbon-12. So the average atomic mass is the weighted average of the atomic masses of the naturally occurring isotopes of an element. To calculate average atomic mass, you have to look at both the mass of the isotopes and the relative abundance of each of the element's isotopes. So for example, copper consists of 69.15% copper-63, so the isotope that has a mass of 63, and it has an actual atomic mass of 62.929601 AMU, and 30.85% copper-65, which has an atomic mass of 64.927794 AMU. To find the average atomic mass of copper, we're going to calculate this by multiplying the atomic mass of each isotope by its relative abundance expressed in decimal form. And then we're going to add the results together. So there's a lot of steps, but I'm going to walk you through one step at a time. So if we take a look at our sample problem, we see that the percent of copper-63 is 69.15%. I want to express that abundance as a relative abundance in decimal form and not a percent abundance. So to get rid of the percent, I divide by 100, which moves my decimal point 2 places to the left. So this gives me a relative abundance of 0.6915. I'm then going to multiply my abundance by my mass for that particular isotope. So for copper-63, my mass is 62.929601. So I put that mass down here. So I'm going to take 0.6915 times 62.929601. I'm going to go through the same steps for my isotope of copper-65. It has a percent abundance of 30.85. I want to get rid of the percent, so I divide it by 100, which moves the decimal point 2 places to the left and gives me a relative abundance of 0.3085. I'm going to then multiply that by the atomic mass of my isotope, which is 64.927794. So when I take 0.6915 times 62.929601, I get 43.515 AMU. And when I take 0.3085 times 64.927794, I get 20.030 AMU. The next thing I need to do is add those two values together. So 43.515 plus 20.030 gives me a total of 63.545 AMU. So the calculated average mass of naturally occurring copper is 63.545 AMU, and this is the mass that is reported on the periodic table. We'll be doing sample problems in class, but please make sure you have this sample problem written down in your notes, and if you have any questions, make sure you ask Mrs. Benke about them in class.